Hi, my name is Kate Sayenka. I'm a professor at Boston University, and today I want to talk about dataset bias in computer vision. So this talk is going to be a fairly high-level overview of what dataset bias is in computer vision, some techniques based on domain adaptation that we can use to solve dataset bias and improve our model performance. And so I'm not going to go into a lot of detail on each specific paper, so this is structured more of as a tutorial rather than a detailed talk about one specific approach. But that said, I have references to each paper that I'll talk about, and you're more than welcome to take a look and see if you have any questions. You can also contact me, and I'll be happy to answer them. Okay, so let's start with the problem itself. So what is this problem of dataset bias? So essentially, this is a problem in supervised machine learning where the dataset being used to train a model is biased in some way, which causes poor generalization to future test data. So suppose that you have a neural network, some sort of convolutional neural network that takes images and predicts object bounding boxes and labels. So you could, for example, deploy this on a self-driving car in order to recognize pedestrians. But now let's suppose that your training data set that the model was trained on was biased towards California. So it's all in fact collected in California. And so here's a representative frame of data from that data set. And now that you've trained your model, suppose that you've deployed the product somewhere else, somewhere perhaps in the northeast of US and perhaps in the winter. So now the input images that your network is asked to label look something like this. And because the network hadn't seen this sort of data at training time, it's very likely that it's going to miss quite a few objects and quite a few pedestrians in this example. So this problem is called the problem of dataset bias, or another name for it is domain shift, where the source data is one domain and now the target data that we get at deployment is called the target domain, and it has a shift in the distribution over the input data has shifted from training to test time. Right, so that's the key definition of the problem. Right, so usually there's some reason why this data set shift occurs, and it's often hard to anticipate how it will change. So in this example, in the source, the training domain, the data looked a certain way because California is mostly sunny. You know, people wear certain clothes there, look a certain way, and then at test time, if we get data from somewhere in the northeast in the winter, the sidewalks may not be visible due to snow. The backgrounds look different again due to not having leaves or grass. People wear heavier clothing, they have hats and so on. So it's difficult to anticipate what exactly the cause will be that will change the data distribution. Otherwise, we could just try to anticipate that and to design our model specifically to handle that shift. But the models I'll talk about today are very general in that they don't need to know exactly what caused the domain shift. They can be applied to solve it no matter what the cause of the domain shift is. So it's agnostic to the cause. When does this data set bias happen? Well, it happens a lot, and it happens a lot in applications where the models are actually deployed in the real world. One example is when a model is trained on one data set and then it's applied to another data set. So in the top example here, we have a training data set that was collected in Germany, and then the test data comes from San Francisco. So you have hills, you have different looking trees and vegetation and so on. Down here we have another example where the data set is a data set of objects that came from product images with white backgrounds and canonical poses, and the model is being deployed on a data set collected from a mobile robot where the backgrounds are cluttered and the viewpoints and lighting conditions are very different. Another example of data set bias is when it's biased to a particular modality. Here, for example, the data set being used to train is RGB, and then at test time we get depth images. And here we'd like to adapt from RGB to depth images, so cross modalities. Another very common example is in robotics, where we like to be able to train policies such as object manipulators to do certain tasks, manipulate objects. In this example, it's to put something onto the scale to weigh it, and ideally we like to train these policies in simulation because it's cheap. It's a cheap source of data, doesn't damage the robot. But then at test time we get real images that look like this. So this is what the robot will actually see, observe from its camera. So we'd like to be able to adapt to this bias from simulation to reality. And here is a very related problem where we're training an object classifier on CAD models, 3D models of objects, and then we'd like to use it to recognize objects in real images. So why is dataset bias a bad thing? So I've already alluded to this before. Basically, it's because it causes a drop in performance. It makes our models less accurate. But here is a concrete example. So here we have 3 different data sets of digits. So the task here is the same. Take this an image and classify it as one of 10 possible digit categories. And if we train a model on one of these domains and then test it on images from that same domain, so let's say we train it on MNIST and then we test it on held out images from MNIST, for all of these domains, accuracy should be quite high with modern CNN, so it should be greater than 99% accuracy. However, if we take a modern CNN and we train it on one of these domains and then test it on another one, so let's say we train it on the Street View house numbers domain down here, and then we apply that model on MNIST, try to classify handwritten digits, we'll see that the performance will be very low, so around 67%, much lower than it should be for that problem if we had in-domain data to train on. So it is a serious issue, and in fact, even between these very visually similar looking domains of MNIST and USPS, there's still a very significant drop in performance. Here's another example. In this case, the task is semantic segmentation of an image into semantic categories like pedestrians, road, street signs, bicycles, and so on. And here you see the input image, which comes from a real domain. It's a real image, but the model was trained on simulated data. And you can see that its predictions are very poor. So it's, in fact, I don't have each class. The red pixels are meant to be pedestrians, and it's recognizing the road as other categories. It's really not recognizing the road at all. It's very confused. And so you can see here the strong effect of domain shift on the accuracy of the model's prediction. So what causes this poor performance on the target domain? Well, there are basically 2 key causes of poor performance, at least the ones that I would like to focus on today. One is that the training and test data distributions are different. So I've already alluded to this before. And so that when your training data and test data have different distributions, your model will not generalize well. There are theoretical results that provide even bounds on sort of how poorly your model's generalization error will be in this case, and it's related to the distance between the domains, the distance between the distributions. Because we're talking about deep learning, in deep learning, the model learns its own feature representations. And so another problem that we might run into is that the model that's trained on source data, so here blue points, this is a visualization of the digit data set in two domains. The blue points are the source domain and the red points are the target domain points. So this model that's being used to extract these features was trained on the blue points. It didn't see the red points at training time. And so you can see that even though it's learned discriminative features for the blue domain, your blue points are being clustered well and apart from each other into different categories. That's not the case on the test domain, on the red domain, because it hadn't learned useful features to separate those images from each other. So those are two causes of poor performance in dataset bias. So what are some techniques that we can use to help us deal with dataset bias? Well, the first technique is an obvious one, and that is that we can collect label data from the target domain, right? This could be feasible, but in many cases it's not feasible, mostly because of cost, and especially if we think about the continuum of visual domains in the world. There could be a very large number of different domains that we might encounter. So this could, in some applications, this could incur additional significant cost. In some applications, it's not really feasible. For example, in robotics, again, if we wanted to collect label data, we would have to use the robot to collect that data, and that's often could be dangerous or it could be bad for the robot. It could break its hardware, so we ideally would like to learn from simulated data. Another technique that we could use is to use a better backbone neural network. So the CNN, for example, if we compare AlexNet to ResNet, ResNet will have a lower drop due to dataset bias than AlexNet. So that's another simple technique, but of course we don't have access to better and better models. We just use whatever is available, and so this is also not feasible. Another idea is to use batch normalization, which will normalize the training distribution, and especially if we do domain-specific batch normalization, that's been shown to have a good effect on performance. Also, some folks have combined batch normalization with instance normalization. That's also a useful technique. Another useful technique is data augmentation. For example, the mix match technique, or other just random crops, different color perturbations, kind of simple techniques that we can easily implement. Of course, the more sophisticated our data augmentation becomes, the harder it is to design and implement, and at some point it becomes, we get into diminishing returns. But some simple data augmentation is always a good thing to try first. Some other techniques we could be applying are semi-supervised methods, because we have labeled data in the source domain plus unlabeled data in the target domain, which is the purview of semi-supervised methods. And one such method is pseudo-labeling, where we use our source trained model to assign pseudo-labels to the target, and we then take those pseudo-labels, or at least the confident pseudo-labels, and add them as training labels and retrain our model. So this is another technique we could use. And then finally, and this is what I'll focus on in this talk, we could be using domain adaptation techniques. All right, so today I want to talk about roughly 5 different topics in regards to domain adaptation. And I'll spend most of my time on the first one and then less time on the remaining ideas, because the first one will sort of set up the main method that we'll be using, and then the rest of them will be variations. So let's start by talking about the main approach that I'll focus on, and that is domain alignment. So this is still a fairly dominant technique in domain adaptation. So before I get into that technique, let's just again formally set up what is domain adaptation. It's a method for adapting a model to a novel data set with no or few labels in that novel data set. So notice here that we're assuming that we have data from this target domain. We have a novel data set. We just don't have labels for that data. There are some techniques that don't assume any data at all. They're called domain generalization, but I won't talk about them today. All right, so here's one example. Let's say we have training data from the simulated domain. In this case, we have data from a game engine. This is a game called Grand Theft Auto. It's a driving game, so it's very easy and quite inexpensive to collect lots of labeled examples of objects from this game. So it's very attractive for us to be able to use this to train an object detector for driving applications. However, we want to adapt it to real data, and we say we've collected some real data from a car by putting a dash cam on the car, but we don't have labels for it. So now the goal of domain adaptation is to adapt our model from the source label data to the target unlabeled data. Another example is adapting from product images, such as backpacks, chairs, other products, where we have lots of labeled data available to us, and then our target domain has unlabeled data of robot images of the same object labels. So the categories are the same, but we don't have labels for the target domain, and we'd like to adapt the model to that domain. So our goal is to achieve high accuracy, good performance on the target domain. So the technique that I'll talk about is called adversarial domain alignment. And the key idea there is domain alignment, and then the way it's accomplished is using an adversarial loss, adversarial learning. But let's just start from a neural network model. So this could be most likely a convolutional neural network, but really it could be any neural network, any structure. And the input to this network is the source data plus the labels. The output, it outputs each label in our source data that it knows about. It tries to classify an image into one of those labels. And we train it using some classification loss, for example, cross entropy. Now, let's separate our neural network into the feature encoder part and then the classifier part. So for the purposes of this talk, let's just assume the classifier, the last layer of the network. And then the feature encoder outputs is the second to last layer, and it outputs some feature representation that's then fed into the classifier that makes the final prediction. And let's visualize features of two classes of the source domain. So let's say here are some features being extracted by the feature encoder. And then we can also draw the decision boundary that the classifier is learning to draw between these two classes. Now, if we now take our unlabeled target data and we apply the same encoder CNN and extract features, they will look like this. So essentially they will be distributed differently from the source domain. And this is again because of dataset shift, the dataset bias in our source dataset. Okay, so what is adversarial domain alignment? Well, the goal here is going to be to try to align the distributions. We're going to try to align the source feature distribution with the target distribution such that they become indistinguishable from each other. Right? So essentially it's removing features. Another way of looking at it is it's going to be removing features from the encoder CNN that have to do with specific domains. Right? So it's learning a domain invariant representation rather than a domain specific representation. Okay, so that's the main idea behind it. It's to learn a representation that cannot distinguish the two domains. So how can we do that? So in adversarial domain adaptation, we're going to do that by introducing another classifier. We call it the domain discriminator. So this is the domain discriminator, and this classifier is going to take features being predicted by the encoder, and it's going to try to label them according to which domain they're coming from. So it's going to have a binary label it's predicting. So did this feature come from the source domain or the target domain? Did it come from red or blue domain? Okay, so we're going to train this discriminator. After we've already trained the encoder on the source data, we're going to now train the discriminator with a fixed encoder. We're going to train the discriminator to minimize its error on this domain prediction task. And then this black line shows a hypothetical decision boundary that the discriminator might have learned at the end of that training stage. Now we're going to do an adversarial training regime where now we're again going to freeze our discriminator, and now we're going to train the encoder on both source and target data. But the encoder is going to have not only the classifier loss, it's also going to have a second loss, which is to confuse the discriminator. So its second loss will be to maximize the error of the discriminator, which means it's going to try to fool the discriminator into not being able to predict the domain of the point. Okay, so there are these two spies acting against each other, the white spy and the black spy. And so after we've trained the encoder CNN, it now might look like this. The feature distributions might become more indistinguishable, but now we go back and we update the discriminator, and we can alternate this procedure for a while. Ultimately, what we'd like to see is upon convergence, the data sets have been aligned and the classifier can do well now on both the source and target domain. Now, this will not always happen for various reasons, and I'll touch on some of those reasons later on in the talk. But this is the basic idea behind adversarial domain adaptation. Okay, so here are some early results of this idea from some of the early work that we've done in this space. And we're going to go back to our digits examples that I showed you before, and this is the source-only performance, which means we just train on the source domain, like the street view house numbers, and then we measure the accuracy on the target domain, like MNIST, directly without doing any adaptation. And so some early results of applying this idea of domain alignment, these are two different methods, has worked to some degree. So in fact, if you look at the later method from 2017, it is now improving on the source-only method, especially for these USPS and MNIST domain shifts, which are closer together. So these are both black background data sets. Still not great on the street house numbers to MNIST shift, but improving. Now, if we visualize now the same features that we had before, now after doing domain alignment, we can see that the red and blue features have indeed been aligned together. So the blue and the red domains are now indistinguishable from each other, for the most part indistinguishable, and this is exactly a direct consequence of that adversarial loss that tries to fool the domain discriminator into not being able to tell them apart. So that idea works to some degree. Now, another idea we could apply here is to transform the source pixels directly to look like target pixels. So apply the transformation not on the feature space, but on the actual image space. So I'll just briefly explain how this works. So we call this pixel space domain alignment. And suppose again we have these Google Street View numbers as our source training data. So this is our label data, and then we want to adapt to MNIST, handwritten digits. So instead of training the source CNN and then using it directly on the target, what we're going to do is we're going to use CycleGAN, which is an adversarial method that takes an image from one domain and translates it to an image in the other domain. So here we're going to use it to generate our training data to look like the MNIST style, right? So we want it to look like it came from the target domain. And you can see that it actually does look a lot like MNIST digits. Maybe they're more noisy in some of the cases, but the important thing is that here we want to preserve the category. So once we have translated our training data to make it look like the target, we now can also apply feature alignment in the feature space of the CNN. So again, we're going to apply the same idea that I just described by adding a discriminator and then fooling the discriminator in order to remove specific features of the domain. So combining these two techniques, pixel space and feature space alignment, turns out that that improves performance. Here's the performance on that Street View to MNIST shift. And comparing to source only or some of the previous methods, you can see that our method, we call this method Cicada, the one that combines pixel and feature alignment, improved performance significantly. However, as you can see, there's still a gap between our method here and the target in-domain performance. So if we could label on the MNIST domain, we would have more than 99% accuracy. So there's still a significant gap there to close. So we can also apply this idea to semantic segmentation. And so here I'm going to show some results of that. Here's another example of semantic segmentation where if we train on the same data set that we test on, in this case the data set is cityscapes, we have some nice predictions that you can see here. So these are the semantic output maps that the model predicts. However, to get this kind of nice performance, we need to label a lot of cityscapes images. And semantic segmentation is a task that is very expensive to label, estimated at around $10 to $12 per image to annotate. So it would be nice if we could now adapt it to new data sets without incurring the same annotation cost. And in fact, if we apply that model directly to San Francisco data, we see that the nice maps are no longer being predicted, and now the model is confusing, for example, cars with road pixels and making other mistakes. So again, we can apply our domain adaptation idea to this problem, and I'll show it to you for the synthetic to real case. So here the synthetic data comes from the Grand Theft Auto game, and the real data is cityscapes. And so here's an example of doing pixel level adaptation for these two data sets. So now this source training image looks like this once it's been translated to the real domain, the target domain. So I'll show it to you again here in video form. So again, now we see the real domain, and now we see the real domain translated to the game environment. And so in the game, you notice that textures of the road are much rougher, and the colors are very different. So it's changing both texture and color as part of this translation. And so again, going back to that example where we tested this model on a real image from cityscapes. So this model was trained on the game, and then when we tested it, didn't do so well. Now with our adaptation technique, we can see that results have improved, especially for the road. So you see here the road is being recognized actually correctly for the most part, although there's still some errors. But overall, this is a better result. But just for comparison, this is the ground truth. This is the human annotation, and as you can see, there's still quite a few errors between the prediction and the ground truth. So we're closing this gap, but there's still some ways to go. In this case, when we measure per pixel accuracy of the source-only model, it's around 62.5% accuracy. So that's measuring how accurately each pixel is being predicted compared to its ground truth label. And then with our model, we get 82.3% accuracy, so we have a significant improvement. But again, if we train a model on the target domain with lots of target labels, we can get up to 94.3% accuracy per pixel. So there is still a gap there, even though we're improving. And then I want to show another example of applying the same pixel level adaptation method to the robotics domain. So this is some recent work that I've done with my collaborators at Northeastern, where our task here is to teach a robot to perform manipulation tasks like inserting a peg into this hole with clutter. So the robot learns in simulation, it has a depth sensor, and so in simulation we simulate what it will see in real life at test time. So we simulate not the RGB, but just the depth images. So we don't actually use RGB input, we just use the depth in this case to control the robot. And so it has to learn to avoid all these obstacles, and it has to be invariant to various amounts of clutter, different positions of objects, and so on. And again, there is a gap that we observe between the simulated depth images and the real ones, which affected performance quite a bit. And so we applied domain alignment to align the simulated and the real depth image data. So here you see a demonstration of the adapted policy for this task. So you can see that even though it was trained in simulation, it's able to handle real data. Now, so far I've talked about adaptation using domain alignment. Now I want to switch to a few more recent directions that I've been working on. And the first one is adaptation for the task of object detection. So far, we've talked mostly about object classification. However, object detection, or we also talked about semantic segmentation, in fact. Object detection is another one of these very common computer vision tasks that can suffer from domain shift. So one problem with object detection is that the scene layout can change between the source and the target domains. What I mean by that is images in the source domain might have different layouts. For example, maybe just one car or one or two cars, whereas in the target domain we might have many cars. And so for training a car detector, this could be a problem because now we're trying to align images with many cars to an image with just one car, and this kind of strong alignment can force the model to remove useful features, to unlearn useful features, to just say, I don't know how to represent multiple cars anymore, or something like that. So we observe that this kind of strong alignment can actually hurt performance when scene layout changes between domains. So the idea that we came up with to address this is to learn to align domains weakly, not strongly. So you can think of it as weak or partial alignment. Right? So this is an illustration of this idea where if the scenes have similar layout between two domains, so here on the left, I'm showing an example like this where the source and the target domain only differ in atmospheric conditions. So they're essentially the same images, but the target has had fog added to it. And so here the scene layouts are very similar, and then our method will align them strongly. But on the other hand, here on the right-hand side, if the scene layout does change, the method will do partial or weak alignment at this global scene level. So this, we call this strong weak distribution alignment. And so when we applied this to several data sets for object detection, we actually saw that it can improve results. Again, we have a source data set, like in this case, cityscapes, and then our target data set is foggy cityscapes. And we show that we can improve object detection. The mean average precision goes up by almost 12% compared to the state-of-the-art method at the time. And again, we see a gap between, on this data set, between our method and the Oracle, where by Oracle I mean we assume access to training data in the target domain. So how well would we do if we had training data in the target? So there's still some gap, but we're closing it. Here we have two fairly dissimilar domains, and again our method works well at closing this gap, improving performance by 13.5% compared to state-of-the-art at the time. So indeed, it turns out we don't need strong alignment. We can get away with weak alignment, and it can be actually more effective in some cases. Again, so I'm going to go much faster now. I'm not going to go into a lot of detail, but I invite you to look at the papers if you're interested. So the next thing I want to talk about is what if we could actually get some labels on our target domain? What is the best way of doing that? And the idea is to combine adaptation with active learning. So this is some recent work where we try to see how well we can do if we not just label some images in the target and then apply adaptation directly, but what if we combine that with active learning? Right, so suppose we have our source data set right here. So these are real images, and then our target data set is these drawings. And so there's clearly a large amount of shift between them. And so rather than just using unlabeled target data as we've done so far, what if we could ask our user to annotate a few examples from the target domain, right? So they could maybe provide 1 to 3 labels per category for us. And then we still are going to use the unlabeled data as well. Or, in fact, can we use active adaptation, which means that rather than randomly choosing examples for the user to annotate, we're going to choose the most informative target examples for the user to annotate. So we're going to combine these two ideas of adaptation and active learning. And hopefully this gives us better results, and in fact that's what we're seeing. So here's a brief overview of this method, which we call CLUE. So we start with the source domain here. This is shown with pink color, and the target domain is shown in blue, and then we start with unlabeled examples, which are empty shapes, and then these shaded shapes are the ones that we select for labeling. So we select these shaded blue shapes and ask the user to label them. So here we designed a way of selecting the best, the most informative examples that will help us learn a better model. Once we've obtained labels. Now they've become shaded because they're labels. So solid color, excuse me, not shaded, solid color shapes are labeled. And so now in the next step, we do domain adaptation, and we use an adversarial technique called adversarial entropy minimization. It's technically different from the one I've described before, but at a high level, it's a similar idea. So we're trying to align the distribution of the blue points and the pink points in this step. And so after this, ideally we have a picture that looks like this, where the blue and the pink points have been more or less aligned. And now we can repeat this process and ask the user for more labels, and then go back to the first step and then the second step and keep iterating. So here's one plot of results where we compare our technique, which is this red line, as a function of the number of labels obtained from the user. So between 0 labels, which is just using unlabeled data alone, and up to 300 labels from the MNIST dataset. This is, again, adapting from the street numbers to the MNIST. And we can see that our method, the red line, is outperforming alternative methods, baselines. For example, this brown line is a uniform sampling with fine-tuning of the source model. So it's a straightforward baseline. And here we're able to do better than that. Then when we look at which examples our method chooses, we see that it's choosing more informative points. So here, these pictures visualize the examples, one batch of examples that was chosen by our method for labeling. And we see that they more often come from solid regions. Here, solid points mean that they're being incorrectly labeled by the source. So these are target points that are being incorrectly labeled by the source. And we see that our method is choosing points from those regions more often than the correctly labeled ones. Of course, we don't have labels. Our method doesn't have access to the labels. That's just for visualization. Okay, so that was active learning. Now I want to talk briefly about another idea, which is, or rather another problem that we encounter, which is category shift. So what is category shift? This is when categories are not the same in the source and target domains. So for example, if our source domain had these 6 categories, and then our target domain had butterfly, berry, and pizza, and didn't have these other 3 categories in it, and we may have no way of knowing that that is the case, right? Also, our target domain might have additional categories, which we'll call novel categories, that are not present in the source domain. So this is category shift. So in addition to a domain shift at the input level, we now also have category shift. So dealing with this turns out to not be straightforward, and the methods I've described so far actually don't handle this very well. So we need to do something else here. And so we've proposed another recent approach to adapting in the presence of category shift. So here I'll first illustrate the problem, and then I'll just allude to what the solution is. I will not go into detail. But here I'm showing you a distribution of features. This is again a t-SNE visualization, and these are images from a data set called Office Home. And they come from 2 domains. So the red points are source features from source classes that are also shared with target. And blue points are those same classes, but in the target. And we can see the large distributional shift between the red and the blue points. Now, these are all points with the same categories that are shared between source and target. The green points are source features that have category labels that don't occur in the target at all. So this is a category shift situation. Now, what happens if we apply our standard domain alignment technique? Well, this is what happens. It tries to it tries to align all the source points with all the target points, and therefore it ends up aligning a lot of blue points with green source points, which are incorrect labels for the target because those are categories that are not present in the target. So we have this catastrophic alignment situation and poor performance. Now, the solution that we propose to this is based on clustering and rejecting outliers. So in our case, we apply a twofold approach. First of all, we apply clustering to these blue points to try to push them into clusters and push them closer to the source points. And then we also, if the points are about to be labeled as one of these green points, which essentially we can tell based on some threshold over the entropy of the point. So we try to reject these green points as outliers while we're doing this adaptation. So the result looks like this. So this is a visualization after adaptation with our method. And here we can see that our method successfully aligned most of the blue points in the target with the red points in the source, which share the same categories, and did not align blue points with the green points, which are the wrong categories for the target. They're not appearing in the target. And again, we didn't tell our algorithm exactly the situation, which kind of shift there was. It just learns to do this on its own, which is nice. So I'll show a few more results. Basically, this is a synthetic to real adaptation problem where the source domain is synthetic images and the target is real images, and we want to classify these objects, but some of the objects are missing in the target. And so when we evaluate our method, we see that it achieves state-of-the-art accuracy on the closed setting. That's the setting where the categories are the same 12 in this case. But in the partial adaptation setting where there's a category shift from 12 to 6 categories, we have a significant improvement of 14% in accuracy. We also applied this method to the Office Home data set that I was showing earlier. These are some example images from this data set. It has 4 domains and 65 categories of objects. And again, we observe here that our method is able to obtain state-of-the-art results on this data set compared to baselines designed for specific settings, for example, designed specifically for closed no shift or for a partial or open set shift setting. Except that in our case, we don't know which kind of shift we'll encounter, if any, and yet we still are able to achieve state-of-the-art accuracy on this data set. So the last thing I want to briefly mention is domain net. So I've shown quite a few different data sets throughout this talk. And so what I want to close with is a new data set that we've collected for this problem of data set bias to allow us and others to have a larger benchmark data set with which we can explore different settings and hopefully improve the state of the art. So this data set is the largest so far multi-domain data set. It contains 0.6 million images, and what's significant about it and new about it is that it has more categories than any previous data set. So it has object categories of 345 object categories and 6 domains. So the domains are shown here, and also show more examples from these different domains. So these are clip art, drawings, sketch, reel, quick draw, which is a Google Quick Draw domain where people are asked to quickly draw different objects, and then infograph is the 6th domain. So as you can see, these are diverse domains. These were collected by searching the web and then cleaning and filtering and annotating the data. This graph shows the number of instances by category. So there are 345 categories, and the colors in the top graph indicate the proportion of instances in each domain. So for example, pink is clip art, green is infograph, and so on. And then the bottom graph shows the number of instances per type of object, where we have grouped objects into types like furniture, mammals, tools, and so on. So this is really going much further beyond just digits or a small number of categories, and trying to create a more diverse and more challenging benchmark. So this brings me to the end of my talk. Just briefly to conclude, I've described the problem of domain bias or dataset bias in computer vision, and I've talked about a few techniques for dealing with domain bias based on domain alignment. So I showed that feature level and pixel level alignment can help using adversarial alignment techniques. I also introduced the idea of weak domain alignment, which can be effective for dissimilar scene layouts, for example, as applied to object detection. I've talked about how we can use active learning in combination with domain alignment to do semi-supervised adaptation, and I've also briefly alluded to the fact that we might have category shift problems, and that's something that we also need to deal with in this setting, and briefly proposed a solution for that problem. So I hope you enjoyed this talk. Thank you very much for listening. And as I said before, if you have any questions, feel free to contact me via email, and I'll try to answer them. Thanks.